Welcome everyone. Let us study characterization of nanoparticles. We all know that nanoparticles, they have the size from 1 to 100 nanometers, and nanoparticles are of different types. They may be carbon nanoparticles, metal oxide, or they may be made up of organic matters. They have different physical and chemical properties, biological properties with respect to their bulk materials. These nanoparticles are of different shapes, size, and having different dimensions. There are also different types such as organic, inorganic, carbon-based materials. Depending upon size, they may be zero-dimensional, one-dimensional, two-dimensional, three-dimensional, etc. When we synthesize nanoparticles for a particular purpose, then it is necessary to characterize that nanoparticles. And for characterization of nanoparticles, there are different methods. Characterization of nanoparticles. Some commonly used characterization techniques are listed in this video. Commonly used characterization techniques are broadly classified into four groups: microscopy based technique, spectroscopy based technique, X-ray based technique, and light scattering technique. In microscopy based technique, the techniques involve SEM, that is scanning electron microscopy, TEM, that is transmission electron microscopy, AFM, that is atomic force microscopy, STM, that is scanning tunneling microscopy, EDX, energy dispersive X-ray analysis, HRTM, high resonance transmission electron microscopy. All these are microscopy based technique. Spectroscopy based technique involves UV visible spectroscopy, FTR, Fourier transform, infrared spectroscopy, Raman spectroscopy, etc. X-ray based technique involves XRD, that is X-ray diffraction, XPS, that is X-ray photoelectron spectroscopy. These are the some X-ray based techniques which are commonly used. Light scattering techniques involves DLS, that is dynamic light scattering, zeta potential, etc. These are the some common techniques by which nanoparticles are characterized. And the characterization is the most important part for the synthesis and for applications of nanoparticles. First we see microscopy based characterization techniques. These optical microscopic techniques are used for morphological studies of nanoparticles. Many researchers use this technique to determine size and shape of the synthesized nanoparticles. That is, for morphological study, microscopy based characterization techniques are used. The first is scanning electron microscopy, that is SEM. It is widely used technique for characterization of nanoparticles. Scanning electron microscopy functions like an optical microscope, but instead of visible light, electron beam is used for microscopy. The electron beam is directed towards the sample. It scans the surface of the particles and gives more resolved magnified image. This is the schematic diagram of SEM. In case of SEM, electromagnetic coils are works as lenses. Due to the very narrow electron beam, SEM micrographs have a large depth of field gives characteristic three-dimensional appearance, which is useful for understanding the surface structure of the sample, that is topography. This method is used for particle size analysis, that is particle size characterization, and the important point to note that for SEM, the dehydrated sample is used for analysis. This is the most important for SEM, and it is used to determine the particle size. The next technique is transmission electron microscopy. In the transmission electron microscopy, an electron beam is transmitted through a very thin film of a sample, and then it passes and interacts with the sample. This is the thin film of the sample. And as the name suggests, transmission electron microscopy, the electron beam is transmitted through the thin film of the sample. And as it is transmitted through a sample, uh, it gives the magnifying image. That image is recorded on a photographic film, and this method is useful for analysis of particle size, morphology, and crystallography of nanoparticles. The next technique is atomic force microscopy. Atomic force microscopy, or AFM, is an ultra high resolution microscopy technique which scans the surface of the sample by contact or non-contact mode using probe tip of atomic scale. This is the probe of AFM, and with the help of that probe, it can analyze the morphology of the sample. It provides the most accurate description of size, shape, and it requires no mathematical treatment. The particle size obtained by AFM technique provides a real picture which helps to understand the effect of various biological conditions. In polymer nanocomposites, it can be used to measure the surface roughness and visualize the surface texture on many types of material. AFM can be used for non-conducting samples without any specific treatment. The next technique is scanning tunneling microscopy, that is STM. Scanning tunneling microscopy technique gives image of surface of the sample with a fine probe with the conducting tip. This is the fine probe of the conducting tip. The quantum tunneling is the working principle behind the STM. We are not going through the working of the STM. We only are going through the characterization techniques needed for nanoparticles. When the sample surface come in contact with the conducting tip, electrons can tunnel through the vacuum between them due to the bias. At low voltages, the tunneling current depends upon the local density of states at the Fermi level of the sample. Lateral resolution of 0.1 nanometer and depth resolution of 0.01 nanometer are considered good resolution in STM. This technique can be used either in air or vacuum or in liquid or gas at various temperature ranges. This is also a morphological technique. The next technique is X-ray dispersive energy dispersive X-ray analysis technique, that is EDX. Energy dispersive X-ray spectroscopy. It is specially used for chemical characterization. This is the sample, and with the help of EDX, we can determine the elemental proportion on the surface of the sample. This technique gives an overall mapping of the sample by analyzing near surface elements and estimates the elemental proportion. EDX is used in conjunction with SAME. The composition of nanomaterial particles near and the surface can be estimated through EDX. An electron beam with energy of 10 to 20 keV strikes to the conducting sample surface, causing X-rays to emit from the material, and the energy of the emitted X-ray depends upon the material under examination. Thus, with the help of EDX, we can determine the chemical composition on surface of the sample. All these are morphological techniques. The next technique is high resolution transmission electron microscopy. High resolution transmission electron microscopy is a TEM imaging mode which gives the crystallographic structure of a sample at an atomic level. Images are created from the interference in the image plane. Defects in the crystal can be imaged by this method. That is, it is a high resolution technique of TEM. Then we see spectroscopy based technique. The sample is exposed to certain kind of radiations electromagnetic radiations such as IR, UV visible, etc. The absorption spectra obtained is useful for characterization of nanoparticles. The most important is ultraviolet spectroscopy. UV visible involves spectroscopy of photons in UV visible region, that is from 200 to 800 nanometer. This is the range for UV visible region. Out of that, 200 to 400 is the UV region and 400 to 800 it is a visible region. UV visible spectrophotometers are mainly used to measure transmission or absorption in liquids and transparent or opaque solids. When a beam of UV light passes through a sample solution, then molecules undergo electronic transitions. We all know that in UV visible, when we irradiate the sample with UV visible light, then electronic transition takes place. Some of the light energy will be absorbed as the electron is promoted to a higher energy orbital, HOMO to LUMO, that is highest occupied molecular orbital to lowest unoccupied molecular orbital. A spectrophotometer records the wavelengths at which absorption occurs, together with the degree of absorption at each wavelength. The resulting spectrum is presented as a graph of absorbance versus wavelength. And this characterization technique is very useful because whether the nanoparticle shows absorption in UV region or in visible region, that is the important part for further research. Then next technique is Fourier transform infrared spectroscopy, that is FTIR technique. FTIR technique is based on measurement of absorption of electromagnetic radiation with wavelengths in mid-infrared region, that is from 4000 to 400 per centimeter. FTIR analysis is used for the identification of organic, inorganic, and polymeric materials using infrared light to scan samples. When molecule absorbs IR radiation, the dipole moment is changed and in some way and the molecule becomes IR active. A recorded spectrum represents the position of bonds related to the strength and nature of the bonds and specific functional groups, thus providing information on molecular structures and interactions. FTIR is useful for identifying and characterizing unknown materials, detecting contaminants in the material, finding additives, and identifying decomposition and oxidation. Only remember that FTIR technique is used to detect the functional groups present on nanoparticles or in nanoparticles. Next technique is Raman spectroscopy. Raman spectroscopy is a spectroscopic technique that uses Raman scattering or inelastic scattering of monochromatic laser light, and it is used to study the rotation, vibration, and other modes of a system. The interaction between photons and a laser light causes a change in energy, and these shifts provides the information about the modes of photons in the system. The electromagnetic radiation from the struck laser is collected with the lens and guided through a collimator. The molecule is excited from ground state to an excited state and is released into vibrating excited state. We have to know what is the basic principle of Raman spectroscopy, that is scattering of light. Then suppose the molecule is already in vibration state, then it gives the Stokes-Raman scatter. There are two types of Stokes shift, anti-Stokes shift that we have to study in detail for Raman spectroscopy. A change in polarizability is necessary for the molecule to exhibit Raman scattering. Then third type of method, that is X-ray based techniques. X-rays are the electromagnetic radiations having shorter wavelength, that is high energy radiations. X-ray diffraction is the conventional technique for determination of crystallographic structure or morphology. These are the high energy radiations used to study the crystallographic structure of the particle. X-ray diffraction. X-ray diffraction is a non-destructive type of analytical technique which provides valuable insight about the lattice structure of the crystalline substance like unit cell dimensions, bond angles, chemical composition, crystallographic structure of natural and manufactured material. XRD is based on the principle of constructive interference of X-rays and the sample concerned, which should be crystalline. The interaction that follows produces constructive interference based on Bragg's law, which relates wavelength of incident light radiations to the refractive angle and lattice spacing. We know that the Bragg's equation. XRD techniques are usually performed in powdered samples. XRD is not suitable for amorphous materials and the XRD peaks are too wide for particles having smaller than 3 nanometers. When we study the XRD of nanoparticles, if sharp peaks are seen, then we say that the nanomaterial is a crystalline in nature. And if uh, wide broad spectra are seen, then we say that the material is amorphous. That is, XRD technique is also useful to determine the nature of the nanoparticle materials. The next technique is X-ray photoelectronic spectroscopy, that is XPS, or electronic spectroscopy for chemical analysis. XPS is the most widely used analytical technique for surface chemical analysis, also used for characterization of nanoscale materials. The underlying physical principle is the photoelectric effect. XPS is the powerful quantitative technique useful for elucidating the electronic structure, elemental composition, and oxidation states of elements in the material. Then last type, that is the fourth type, is light scattering techniques. The interaction of light with matter gives information related to the physical characteristics of the sample. The dynamic light scattering, DLS. The detection of light scattering from the interaction of light with matter gives information related to the physical characteristics of the sample. In light scattering experiments, a monochromatic beam is directed to the sample and then a detector records the scattered light at a certain angle. Characterization of colloidal solutions and nanoparticles is carried out with the DLS. This is a useful technique to evaluate particle size distribution of nanoparticles in solution. This technique is also useful to detect whether nanoparticles are aggregate or scattered in the solution. The next important technique is determination of zeta potential. Zeta potential is a measure of effective electric charge on nanoparticle surface and quantifies the charge stability of colloidal particles. This potential is an indirect measure of the surface of the charge. It corresponds to potential difference between the outer Helmholtz plane and the surface of shear. High zeta potential values, either positive or negative, should be achieved in order to ensure stability and avoid aggregation of the particles. The higher magnitude represents increased stability due to increased electrostatic repulsion. The extent of surface hydrophobicity can be predicted from the values of zeta potential. In short, if zeta potential is higher, aggregation will be less. That is important. Then we summarize that all this technique. The characterization technique for nanoparticles, which technique should be used for which purpose. The parameter to be analyzed and suitable characterization technique. For particle size, the suitable characterization techniques are SAME, TAME, HRTM, AFM, XRD, DLS. All these gives information regarding particle size. For particle shape, suitable technique is TAME, HRTM, AFM. For crystal structure, technique is XRD, STEM, STM, HRTM. For chemical composition, the technique used is XRD, XPS, SAME, EDX. For particle size distribution, technique used is SAME and DLS. To determine surface charge, we have to determine zeta potential. For optical properties, UV visible, fluorescence, etc. For aggregation, DLS, zeta potential, UV visible, etc. And for surface functionalization, the technique used is FTIR. These are the some common techniques used for characterization of nanoparticles. Nanotechnology, it is a wide subject. The number of parameters we have to analyze, but for beginners, the nanoparticle should have to be gone through that characterization techniques. Thanks for watching this video. Thank you very much.